So another way to describe a set is to include all elements of a larger set that satisfy a certain condition. And here's the notation. This is read as A is equal to the set of all x in S such that P of x. So S is the larger set from which the elements in A are taken, and P of x is some condition. This symbol, bar, is just read as such that. So like I said before, this would be read all x in S such that P of x. So for example, C can be all the elements x and z such that 0 is less than x is less than 100 and x is prime. So these are all prime integers between 0 and 100. The first statement, x is in z, indicates that we're dealing with integers. And then we need them to be between 0 and 100, and we need it to be prime. This set D, which is the set of all x in R, such that the absolute value of x is less than 1, is all the real numbers between -1 and 1, not including those boundary points. So now we're considering all real numbers, and we need anything with an absolute value smaller than 1. The universal set, which is usually denoted by U, is the set that contains all elements mentioned in a particular context. So for instance, my last example, the universal set would be the real numbers since I was considering the elements of the real numbers whose absolute value was less than 1. So for another example, if we want to consider certain types of real numbers, it would be understood that any element is a real number. So that is the universal set. If we're discussing academic standing of certain students at a school, the universal set would be all students enrolled at the school. And if the universal set isn't clear, we can identify it. We often represent sets pictorially with Venn diagrams. So we use a rectangle to denote the universal set U and oval shapes to denote the sets. And sometimes they can indicate which specific elements are inside and outside the set. And it's an element's drawn inside the oval if it is inside the set represented by the oval. So here's a picture. Any elements in this orange part would be in A. Any elements in the blue part would be in B. Any elements in this overlapping area would be in both A and B. And anything outside these two circles would be in the universal set, but not in either one of the sets. If we have every element in A is also an element in B, we say A is a subset of B. And this is the notation. If there's something in A that's not in B, A is not a subset. So if the universal set is U, then for every set A, the empty set is a subset of A, which is a subset of U. And we say two sets are equal if and only if each is a subset of the other. So A is equal to B if and only if A is a subset of B and B is a subset of A. A proper subset. So if A is a subset of B and there's an element of B that is not an element of A. So basically we know these two sets are not equal. We say A is a proper subset of B. We have a different notation for that. And you'll notice the only real difference between these two notations is the bar underneath. You can kind of think of it as a less than or a less than or greater, a less than or equal to sign. The bar just indicates that it is possible that these two sets are equal. Here's a diagram. As long as there is something inside the blue part, then it's a proper subset. If everything inside of B is contained inside this purple circle, they would be equal. And it's possible that the elements of a set are a set themselves. So here's a set, A, which is the set containing 1 and 2, the empty set, the set 1, 2, and 3, and the set of just 1. So 4 elements, which I just listed. Note that 1 is not in the set A. However, the set containing the element 1 is in A. And the set containing the element 1 is not a subset because 1 is not in there. The empty set is not the same as the set containing the empty set. The cardinality of the set containing the empty set is 1, since it contains an element, the empty set. And a set can contain a combination of numbers and sets in a number. So for instance, here's a set B. 2 is in B, but 1 is not. Also, the set containing 2 is a subset of B, but the set containing 1 is not a subset of B. And the power set of A is actually the set of all subsets. So for example, if A is equal to the set of 1, 2, 3, we have the power set would be all possible subsets. The empty set is a subset of any set, so it's included. We have what are called singleton sets, sets containing one element, so 1, 2, and 3. We next are going to look at sets containing two elements, so this would be the set of 1 and 2, the set 1, 3, and the set 2, 3. And then finally, the set containing all three elements. And in general, if the cardinality of A is n, the cardinality of the power set is going to be 2 to the n.